Thanks, Joshan, and thanks to the organizers for the opportunity to speak. So today I want to talk about work I did in collaboration with Laura Johnson, who's a postdoc at ETH Zurich, and Callum Jones, who's a postdoc at UCLA, who's also giving the talk right after me, actually. So it's based on work that's in this preprint over here. And the basic goal of the paper and this talk is going to be to study a naive extension of the BCJ double copy that we all know and love. And in particular, if you naively add mass to to this BCJ double copy, then do the resulting amplitudes, do they factorize correctly? Are they local appropriately? And also what happens to them in the massless or the decoupling or the high energy limit. And I will use those three terms kind of interchangeably. Um, so the example the primary example that we'll be looking at is massive Yang mills and studying whether massive Yang mills squares to a theory of massive gravity. Um, so I should say that we're not looking at a completely general setup. So throughout this talk, I'm going to be at tree level, and I'm going to be looking at particles in the adjoint representation. Also, massive or the double copy of amplitudes with massive particles has been studied before, typically in slightly more special contexts where you have some massless particle in your spectrum, or you're looking at particular amplitudes in your theory. So here we want to take a very general approach and see um, what we're even allowed to double copy if you look at a general massive extension of BCJ color kinematics. All right, so let's start. So this is the vanilla massless BCJ. You have your color factors and numerators, and your numerator satisfies some kinematic Jacobi identity. At 4 point, this just looks like ns plus nt plus nu is 0. And as we know, these numerators aren't unique because they have some generalized gauge freedom. So if I do this generalized gauge transformation over here, I'm going to leave my amplitude invariant, and also I'm going to leave my kinematic Jacobi identity invariant. So I can go from one BCJ form of the amplitude to another via this one function delta's worth of um, stuff, so freedom, right? So let's now do the naive massive extension, meaning that I'm just going to take these propagators and add a mass to them, right? And also I'm going to think of this amplitude as now having massive external states. Good, so then this is the form of the amplitude, right? And if I can find a kinematic Jacobi satisfying form, then, well, I still have some generalized gauge transformation under which this amplitude is invariant. But what happens is that the kinematic Jacobi identity is no longer preserved. So by doing this generalized gauge transformation, I go from a BCJ form of the amplitude to a non-BCJ satisfying form of the amplitude. Okay, so what this means that in this massive case, you have no generalized gauge freedom. A corollary of this statement is that if I started with a set of numerators that don't satisfy kinematic Jacobi, I can always do a generalized gauge transformation to get a set of numerators that do satisfy the Jacobi relation. So basically, this means that in a massive theory, at least at 4 point, as we've demonstrated so far, color kinematics is trivial. In the massless case, this was a hard thing, and you wanted to find theories which did satisfy this in order to double copy. But in this case, it's just a trivial fact that you can always find color kinematics satisfying numerators. So let's actually find them. So the way we're going to do this is we're going to write partially color ordered amplitudes as the product of some propagator matrix times a minimal set of numerators, right? So I've just removed nu because I can always calculate it using the kinematic Jacobi identity. Good, so then I look at this matrix and it's full rank, which means I can just invert it and I can find the unique answer, which is the numerators that correspond to this massive theory with these spatial color ordered amplitudes. So so various things to note here. In the massless case, this matrix would have not been full rank, right? It would have been non-invertible, and the null vector would would have been the reason you have a fundamental BCJ relation in the first place. So in this case, because you have no null vectors, you have no BCJ relations. Um, Another thing that's interesting to see at 4 point is that there are no extra poles that are generated by this inversion process. So I'm not going to run into a problem of double poles when I use this formula. Good. Some of you though might complain that sure there are no kinematic poles, but there's this 1/m square sitting out there, and that's kind of ugly, and I don't like that. So so I would argue that the way one takes massless limits, you need to be careful about, because in a naive m goes to zero limit, usually things are ill-defined, especially when you're looking at a higher spin thing. Higher spin meaning non-scalar thing. So as an example, let's look at the massive photon. So the massive photon, of course, has 3 degrees of freedom, and in the massless case, if I just sent m to zero, it would have 2 degrees of freedom. And so clearly there's some loss of degrees of freedom that I want to avoid. And the way to avoid that is via what's called the Stuckelberg trick, or the Stuckelberg replacement. So when I do this replacement, then it becomes obvious that there are these 1/m's floating around, which, so I can no longer just take m to zero in my Lagrangian, right? So this is telling you why, because there's some mode that you're going to lose. So the right way of doing this, where you don't lose degrees of freedom, is to keep this the most singular coupling fixed while taking a double scaling limit where the coupling and the mass both go to zero. So this is what's called the decoupling limit. And this is what I mean when I say the massless limit. Um, yeah, so clearly over here, what's happened is that the longitudinal mode of this massive photon has now become the scalar field that has some nonlinear self-interactions. Okay, so as I said in the beginning, what we're interested in is a massive gluonic or a massive Yang-Mills theory. So all I'm going to do is take this Lagrangian and decorate it with color factors, meaning some A index, which is now a color index, right? So I'm going to look at a Lagrangian that looks like this. And in the decoupling limit, again, my longitudinal mode is going to look like some scalar field. And the Goldstone-Boson equivalence theorem tells us that those scalar self-interactions will just be a nonlinear sigma model of some pions. All right, so this kind of motivates now why one would even try and look for a double copy that connects massive Yang-Mills and massive gravity, right? Because if you take the decoupling limit of massive Yang-Mills, you get the nonlinear sigma model. And you know that the nonlinear sigma model can be double copied to give you special Galileans. Additionally, special Galileans come from the decoupling limit or arise in the decoupling limit of massive gravity. So that kind of might lead one to speculate that massive Yang-Mills and massive gravity are connected via these massive BCG relations. So for the remainder of the talk, I'm going to explore whether this speculation is reasonable and to what extent it works and doesn't. So our broad strategy for doing the double copy is going to be to calculate the partial amplitudes. In this case, we were low enough point that we could just use the Feynman rules and didn't need any fancy anything. So we then invert that matrix of ours to then calculate the BCG numerators. The state map is going to look like these two massive vectors, which will then double copy to give one massive graviton with 5 degrees of freedom, a massive dilaton, which is the one over here, and then this anti-symmetric 2 tensor field, which in 4 dimensions is dual to a massive spin 1, so that's just 3 degrees of freedom. So once you build this state map, you can build projection operators, you can calculate amplitudes with different external states. And that's going to be crucial to check the factorization of these higher point graviton amplitudes, which is what we're interested in. Do these things factorize correctly? All right, so let's kick it off. So at 3 point, it's very trivial to see that the double copy works. This is the massive gluon amplitude, and you square it, and that's the massive graviton amplitude with external gravitons. So yeah, I should say that there's some mapping obviously between G and M Planck that I've done over here, and that mapping will continue at higher point. I've also used the convention over here that the the graviton polarization tensor I've split up into these two vectors, polarization vectors. Um, yeah, so that's what these epsilon 1, 2, and 3 are. So now that we have this amplitude, you can project out various different states. And in particular, you can look at the 2 graviton, 1 dilaton state, right? Sorry, amplitude. And, and in the massless case, this vanishes. And here it doesn't, which means that dilaton parity is actually violated in these massive theories. In particular, that means that we can't ignore the dilaton when looking at all graviton external states. So B parity is preserved, so we can pretty much forget about the B field for the rest of this talk. Okay, so let's move on to 4 point. At 4 point, we're in luck because actually the Feynman rule just directly gives you a set of numerators that satisfies kinematic Jacobi. So you just plug it into this formula and it gives you a 4 point amplitude. And that 4 point amplitude matches exactly ghost-free massive gravity 4 point amplitude that was, and this theory of massive gravity was first written down by Diran, Gabadadze, and Tolley, hence the name DRGT, massive gravity. So yeah, it's a healthy theory. It factorizes correctly into the 3 point amplitudes, and everything is, well, it's just peachy. I should mention that in the same week that we put out our paper, there was a paper by Momeni, Rumbutis, and Tolley, where they found the same result as well, that at 4 point this double copy is indeed healthy. So let me just throw back very quickly to the decoupling limit. So as I said, in the decoupling limit, longitudinal gluons are going to look like pions. And if the massive double copy and the decoupling limit commute, one would expect that the longitudinal modes of the graviton will look like special Galileons, and nothing else will be non-zero. So nothing else will survive in that limit. And while we find that the 0, 0 modes do actually look like the special Galilean amplitude, which some of you might recognize as S times T times U, we also find these mixed in between scalars and tensors. So this version of the massive BCJ relations the massive BCJ double copy doesn't commute with the massless limit. Of course, this would have been nice. It would have been nice for it to happen, but it's not necessary for the amplitudes to be local, the resulting amplitudes to be local. So we are going to power through and move on to 5 point and see what happens there. So here things get messy and we start needing to use some numerical values and to study the singularity structure. But the result is that we find that the 5 point amplitude factorizes correctly on all physical poles. And this I think is remarkable, or rather I thought it was remarkable until we found that using the KLT form, you can actually prove that any amplitude built in this way will always factorize correctly on physical poles and will always have the correct physical pole structure. So this might lead you to believe that one can actually do this double copy. But this is kind of where the good news ends. So because yes, we have the right physical poles and factorize correctly, but we also have spurious poles. And this is what the spurious pole structure looks like. It's some quartic messy polynomial in the denominator. And you can calculate the residue on this pole and you find that it's non-zero. So what this tells you is that despite first appearances, this double copy doesn't work. So no, massive Yang mills cannot be double copied to massive gravity. This is disappointing, but it also opens up a lot of questions, right? Which is, Why did this happen? Because there was no extra relation that my theory needed to satisfy to give me a good double copy. That's what we found, no BCG relations.
This is
This
50-minute
actually,
mark. 50-minute mark.
cool, thank you. So this actually stems from the way that we constructed the numerators. So we constructed the numerators by looking at this matrix of propagators, right? And obviously, the matrix of propagators can't contain any spurious singularities, but its inverse can. So the inverse is going to be some matrix of cofactors over the determinant, and cofactors can never have spurious singularities because they're just products of sums of propagators. But the determinant can. In particular, the numerator of the determinant is what we're interested in. And we find that at 5 point, that numerator actually is this horrible quartic polynomial that we found as a spurious pole in our massive gravity amplitude. So having this spurious singularity in this M inverse matrix doesn't mean that you can't have a local construction that comes out of it. It just means that there's an extra condition that needs to be satisfied, which is the cancellation of this spurious polynomial. Um, but what we can say for sure is that this extra cancellation did not happen in the case of massive Yang-Mills. Okay. Um, so this this led us to the question of whether there was a different way of getting rid of these spurious singularities, which was prettier than this horrible looking polynomial. And this is only at 5 point, right? So so what we did was we generalized the spectrum of particles we were looking at. We looked at different masses in our spectrum and looked at the scattering of these masses. So here, this is just an illustration at 4 point. So I'm looking at a theory with these external states M1, M2, M3, and M4, and you're only allowed to exchange one mass on each um, factorization channel. And we found that the condition for spurious singularities to vanish was this quadratic condition on the masses over here, which we dubbed the spectral condition. And this is clearly not satisfied if you have only one mass in your spectrum because you have 3m squared on one side and 4m squared on the other. And so this kind of, in hindsight, explains why this double copy of massive Yang-Mills didn't work. It never could because it doesn't satisfy the spectral condition, nor does it cancel the spurious poles. So I think Callum will talk more about the spectral condition and this minimal rank condition, etc. But I just like to say quickly that it is satisfied by amplitudes and theories that have been studied before in the literature. So this kind of tells you why, when people studied Compton amplitudes and dimensional reductions, that the double copy worked. So this is just a little table that you can have the two ways of getting local double copies, one by the spectral condition, one by canceling spurious poles. But the spectral condition gives you these other nice properties, which is like associated massive BCJ relations, and it commutes with the massless limit. And this more ad hoc spurious pole cancellation doesn't. We also don't know of a theory that cancels these spurious poles except for massive biojoint scalar theory, which is slightly trivial. So that actually leads me to my last slide, which is what happens next? What do we do with this? And I think it left us with maybe more questions than answers, because the first thing on this list is really what are the theories that satisfy both these conditions? What kind of theories can give you a local double copy? In addition, and we have the JHEP reviewer to thank for this, probably out there is my guess. But anyway, is that this spurious singularity polynomial over here is actually proportional to 3D gram determinant. So it vanishes. And so you don't get some amount of the spurious pole structure in 3D. And that leads us to the question of whether this actually is healthy in 3D. Finally, there's the technical question of how to generalize this spectral condition when you have more than one mass that's allowed to run in a channel. Which is not true for at least a very simple KK tower. Yeah, so I think let me end here. Thanks for listening, and I'd be happy to take questions.
Okay, yeah, thanks, Shruti, for a very nice talk. And it's also perfectly timing. So are there any questions? Please raise your hand. Zvi, please.
Yeah, hi, that was very nice. So if you start with the spontaneously broken theory, including the Higgs,
Mhm.
and you just go through that, what happens? You encounter any problems, or does it work automatically?
So I think we expect it not to work, and I think this is something that Laura is working on, which is to understand exactly what doesn't work when you start with. So basically, with the massive Yang-Mills, you start with some theory, and then you Higgs it, and that's how you get the massive gluon. And that's something that maybe she can speak more about it, but we expect it not to work, but we don't know quite what goes wrong.
Okay, thanks.
And Alex?
Maybe I can add to that. For a joint Higgs field, it has been proven that it works. So whenever you have a Coulomb branch Yang-Mills, for example, then it works.
Alex?
Yeah, hi. I must have missed something, but I actually missed the place where the spurious poles started to occur, because at 4 points you seem to have everything working perfectly well, and then suddenly at 5 points they occur, or
Yeah, that's right. So when you do basically this procedure, except at 5 point, you find that the denominator now has this spurious singularity structure, which is exactly the spurious singularity structure, which comes from the determinant of the matrix of propagators.
but then you were showing the spectral condition that was at 4 points.
Yeah. So actually at 5 point, and we speculate also the higher point, that you just take the spectral condition and you apply it to every 4 point subgraph of your amplitudes, and that takes away the spurious poles.
Yeah, but at 4 points, is it satisfied? It looks like you're going to get 3m squared equals 4m squared. So it doesn't seem to work even at 4 points, but you said that it works at 4 points.
Well, yeah, so because in that, I guess this basically what I'm trying to say is that there's two different ways of doing the massive double copy. One is to use the spectral condition, and the other is if you don't have any spurious poles, right? And at 4 point, you just this determinant of m has no spurious poles, so massive Yang-Mills does trivially cancel all the spurious poles in the denominator, so it's
Right.
held. Whereas
Okay.
at 5 point, that doesn't happen. So the only other way it could have worked is if it satisfied the spectral condition, but we find obviously, as you said, because 3m squared doesn't equal 4m squared.
Yeah. Okay. Yeah, that's what I missed. Okay. Thanks.
Okay, and James?
Okay, sorry. Can you say, do you know if the spectral condition can be obtained from some slightly unusual KK reduction?
Yes, I mean that's an interesting question. The one that we looked at was very simple. It was just integers, so you just do an S1 dimensional reduction. I think that's something we want to look at, but we haven't looked at yet. It's an interesting question.
And can you, have you looked at if you add other states to the spectrum?
You mean in massive Yang-Mills?
Yeah.
So no, we haven't. One thing we did try a bit was to add higher derivative corrections, because possibly those could cancel this polynomial over here. We didn't find anything, but we also didn't do a very exhaustive check. So yeah, that's why that's one of these up next questions over here.